Okay. And another important thing is so this Wednesday we will have quiz 1. Okay. Actually, this is 27th of September, and after the holidays, this lecture is after the Wednesday class, after the holidays. This is Wednesday class. This class will be also in video lecture. Okay. You don't have to be here, right? Okay. So we will conduct this as the video lecture as before. I will upload the recorded video in the YouTube. Okay. So you can watch this. Okay. And let's meet from this date. Okay. So you will have long holidays, right, after this Wednesday. Okay. And maybe soon the code assignment 1 will be noticed to you soon, maybe before the holidays. Okay, the deadline would be for 1 month. Okay, I'm expecting that this is not that hard, but basically they are the assignments for using OpenCV and the PyTorch. Okay, so you have to make some data using OpenCV library, and also you have to train some network using the PyTorch library. Okay, that's for code assignment 1, and will be announced soon, maybe before the October. Okay. Okay, this is some announcement before the lecture, and today we will learn about how we can do the segmentation and the pose estimation tasks using the deep learning networks. Okay. So these two, segmentation and pose estimation, those are also important tasks in computer vision. But this class will be more focused on the object detection pipelines, but will deal with these tasks for this, during this class. Okay. Okay. So this is the segmentation task. So if you capture the object using some bounding box representation, inside the bounding box, there are still some pixels which is not belonging to the main object, okay, inside the bounding box. For example, here, this bounding box is capturing the car mainly, right? But there are pixels which is not belonging to the car, okay? So for example, these pixels are belonging to road. 혹시 성함이 어떻게 되죠? What's your name? Okay, thank you. And these pixels may belong to the building pixel, right? And so on. So in this segmentation task, our aim is to pixel wisely classify the object. Okay, we want to capture object more precisely. Okay, so that's the segmentation task. Okay, and also you will see this kind of tasks as well for the computer vision application. So from the RGB image, we can reconstruct this type of pose representation. And also sometimes we want to reconstruct the hand 3D meshes, okay? And for humans, we want to sometimes do the similar things by reconstructing the full 3D meshes of the human body, okay? So now this kind of 3D reconstruction is quite popular. Okay. So this is called as the pose estimation. So if you are reconstructing hand meshes or the hand skeletons, it is called as hand pose estimation task. Or if you want to reconstruct some human mesh or human skeletons, then that is called as human pose estimation task. Okay. So nowadays, this kind of application is also popular. So we will tackle that in this lecture. Okay. And when you understand their pose, this representation, the skeleton or the human mesh, could be rolled as the basic block for further understanding their actions or gestures. Okay. So this pose estimation is because of that, because of their wide applications, this task is getting popular nowadays. Okay, and I will explain you how we can achieve this semantic segmentation task. As I mentioned you, this semantic segmentation, what they do is from images, from image input, we want to calculate their semantic labels for each pixel, okay? So these regions are belonging to the sky class, okay? And these regions, they are belonging to the cat, right? And so on. So for each pixel, we want to reveal their semantic labels, okay? That's what semantic segmentation does, okay? And this is the slide showing that how this semantic segmentation could be achieved, okay? So in previous method, using the conventional machine learning algorithms, indeed, we do semantic segmentation using this method. So for classify this center pixel, we capture some patches like this. Their patch size is, for example, 8 by 8 or 16 by 16. Okay. So anyway, we capture some patches around the center pixels. Okay. And we input this to some classifier and recognize their semantic labels, okay? And then slide these patches right or down, okay? And by doing that, we can classify each pixels in the images, okay? Before deep learning, we indeed do this using some random forest algorithm, which is very fast actually. So we could achieve this semantic segmentation efficiently using the random forest and using this type of features. Okay. 혹시 지금 오신 분 성함이 어떻게 되죠? 김현유. Okay. But the CNN is quite slow, and if you do follow this approach, let's say the width is having these pixels and height is having these pixels, then you have to apply CNNs for each pixel. I mean, this amount of pixels, you have to apply CNN architectures, CNN operations, okay? Then it would be very slow, right? So it may take a few hours to segment out just one image, okay? This is very inefficient. And if it takes too much time for doing the semantic segmentation for just one image, it would be better using our head, right? So the computer vision researchers become to propose some new method, find their motivated to find a new way to achieve this semantic segmentation. Okay. So from this patch, this is the extracted patch, the small sized patch, for example, 16 by 16, and this is the CNN, pre-trained CNN, and this would output the semantic classes. This is the conventional way, but the computer vision researchers become to think about new idea to achieve this semantic segmentation efficiently, okay? So they think of this kind of architecture. So this is similar to our previous CNN architecture. So given input, given 2D input, the CNNs, they tend to reduce the size of the 2D signals, okay? And eventually they flatten it and apply the linear operation to map it to the semantic labels, okay? But in semantic segmentation, the final output may be like this. So its size is same as the original input, but it may have some semantic labels index, okay? So let's say this is 0, and this is 1, this is 2, and this is 3, like that, okay? This index may indicate some semantic class label, okay? But we need same dimensional output as the input dimension, okay? This should be some our desired case, okay? But at this time, we don't know which operation could be here, okay? This operation should upsample the previous signal, right? I mean, opposite to the convolution operation or the pooling operation, these operations have to upsample the input signal. And I mean, the output signals of these layers should be larger than the input signal, okay? And at the same time, they have to be differentiable, okay? To be located between the input and output inside the deep learning architecture, the condition is the layers should meet this condition. They have to be differentiable, right? They have to calculate the differentiation of the output with respect to the input, and differentiate the output should be differentiable with respect to their parameters, okay? This is condition we have to meet for the layers in the middle of the deep learning architecture, okay? So computer vision researchers searched for which operation could be like this, okay? And the solution is this operation, the transpose convolution operation, okay? This operation is quite similar to the convolution operation, and but they are opposite to the original convolution operation. They can upsample the 2D signals. And at the same time, because they are composed of mainly these two operations, the multiplication and addition, so they are differentiable, okay? So we could use this transpose convolution for this part, okay, to upsample the 2D signals to make it similar, make it to have the similar dimension as the input signal, okay? So then I will explain what is transpose convolution operation is. So, but before that, I will explain about the convolution operation. So the blue pixels, this is meaning the input image. And the gray one, this gray 3x3 gray signal, gray visualization, that it is indicating the filter corner of the convolution operation. And by applying this filter corner on this input image and multiplying their coefficients and image pixel values, and by adding them, we can calculate the 1 pixel in output map. So this is the output map, right? I'm assuming that all of you are familiar with convolution operation already. So this is the convolution operation, okay? And because we already enlarged the input image size by applying padding. So this dotted line is meaning the padded regions, zero padded regions, okay? This is having 0, right? So because we do zero padded, the convolution operation starts from here, right? Without zero padding, the convolution operation have to start from here, right? Anyway, so because thanks to the zero padding, now in this figure, the output dimension is same as the input dimension, right? But if we do not use zero padding, or if our stride is larger than 1, then we will, for example, if the stride is 2, then we will move the filter corner by 2 pixels, okay? Then the output size would be halved, okay? Okay, anyway, in this case, the stride was 1, right? We move the windows by 1 pixels, okay? Anyway, the convolution operation tend to reduce dimension of signals, okay? But this transpose convolution operation does the opposite, okay? So it can enlarge the dimension of the input signal when calculating the output signal. So, but their operation is quite similar to the convolution operation. So, samely as before, this green is denoting the output map, and blue is denoting the input map, and gray is the filter corner, okay? And here, the input size is only 2 by 2, okay? But the output size is 4 by 4, okay? So it is upsampling the input signal, okay? To have the enlarged output signal, okay? And what they do is same as the convolution operation. So they apply filter corner here first and multiply its corner coefficient and image pixel values element wisely, and by adding them, we can calculate the first output here, okay? And by shifting the window to here and do same thing and calculate the next output value and so on, okay? This is the transpose convolution operation, and because of that operation, they are mostly composed of these two operations, the plus and multiplication. So they are differentiable, okay? The output is differentiable to the input, and the output is differentiable respect to their parameters. The coefficient, filter coefficient is now the parameters, okay? Anyway, they are differentiable. Okay. So this is showing the transpose convolution operation with zero padding and stride 1 and using the 2 by 2 corner, okay? So this is the corner having 2 by 2 dimension, and this is the input signal, okay? Then when we apply transpose convolution, we by default apply 1-0 padding. Even though we set 0 padding, we by default apply 1-0 padding. So around the image, the red is denoting the input image. And around the input image, we pad 0 one time, okay? And then we apply this 2x2 corner with stride 1, okay? Then we can obtain this 6x6 signal. So input image was 5x5, but the output signal is now 6x6, okay? And this is the code you can use already implemented in the PyTorch. So you can use this for implementing transpose convolution, okay? Anyway, the output signal is enlarged, upsampled compared to the input signal, okay? And now we will see when the stride is changed to 2, okay? And we will see the input was 3x3 case, okay? Even though the input size was 3x3, when the stride is set as 2, then the pixels are located like this with some stride. The input signals are located like this, okay? With one, because the stride is 2, the input signals are having some stride, right? Having some different meaning compared to the original convolution operation, okay? And then we apply this 2x2 corner on this enlarged to this signal, okay? So the output is now again 6x6, and you can see the output signal is upsampled from the input signal, okay? And if you have padding parameter, then the result becomes like this. So we will apply the default 0 padding around the image. So this is the enlarged image by default, in default applying the 0 padding. So we can obtain this amount of signal. But because we set 0 padding as 1, that amount is actually removed. Okay. So in transpose convolution, 0 padding has also different meaning. So it actually removes 0 padding, 1-0 padding, okay? This parameter is actually removes 1-0 padding, okay? So the output size is actually reduced when using zero padding, okay? So anyway, you can notice that transpose convolution, they are having slightly different characteristics to the convolution operation. And they tend to enlarge the signals, okay? Okay, and I will tell you why they are called as the transpose convolution operation then. Okay, so when you have this 4x4 input image and have the 3x3 filter corner, then by applying these filter corners 4 times like this, you can obtain this kind of output, okay? By applying filter corners like this and do element-wise multiplication, these paired signals are multiplied and they are also added to output this 1 to 2, okay? And then we will move the windows right by 1 pixel and do the same to output this, right? And the next, the windows are located here and they are element wisely multiplied. And also when we add them, we can obtain this number and so on, okay? This is the convolution operation, but we can implement that using the matrix multiplication. So, and also indeed in the computer, when implementing this convolution operation, we implement it like this. So this is rather sequential, right? Hard to parallelize. So in PC, we implement the convolution using this type of matrix multiplication. So for doing that, we flatten the input signal. This was the 4x4 matrix, but we flatten it as the 16-dimensional vector. And also the filter kernel was 3x3 signal, but we make it as the convolutional matrix like this. And eventually we multiply this convolution matrix with the flattened input signal. And then we could have 4x1 output vector. And if we rearrange this as the 2x2 matrix, then that will be identical to this output, okay? So actually, this is the way the convolution is implemented in the computer, okay? But then I will say why this transpose convolution is called as transpose convolution. So if we, our original convolutional matrix looks like this, having wider columns than the rows, but we can find some transposed matrix from that, okay? And if we transpose our convolution matrix and multiply the original signal, then we can get enlarged dimensional output than the input, okay? So if we transpose the convolution matrix, the output signal is having larger dimension than the input signal, right? And at the same time, they are differentiable, okay? So if we rearrange this 16-dimensional vector to 4x4 matrix, then this would be now the output of the transposed convolution result, okay? So are you guys following me? Okay. So this is why they are called as transposed convolution, and also they could have this kind of characteristic because of that, okay? And also they are becoming differentiable, okay? So now we could use this transposed convolution operation in the later part of the CNN architecture. But the former part, we will use the convolution operation to kind of extract some feature in the middle of the network. This feature will capture some global information of the images. And then we upsample this feature to obtain this type of segmentation mask, okay? So this is the how we can achieve this semantic segmentation task, okay? So this is the widely used encoder-decoder architecture. So we call this former part as the encoder, okay, we encode the overall images into feature, right? So they are called as encoder. And this part is called as decoder. We decode this feature vector again to the input signal dimensional output. So they are called as decoder. So encoder is composed of the convolution operation, and decoder is composed of the transposed convolution operation. Okay, and in the middle, we have the nonlinear layers. Okay. And forward rule is defined like this. So we input the signal X, apply the encoder first and decoder next, and return it like this. Okay. This is the implementation of this encoder-decoder architecture. Okay. And this is the example of making the segmentation network using that encoder-decoder architecture. So if you change this number, then this is the final output. Final output channel number. So each channel could be the probability for each object. And you can, by changing this num obj, you can decide the number of objects for the segmentation task. Anyway, by training this network and supplying input image and their corresponding segmentation background truths, you can train this network, okay? And by doing this, you do not have to apply CNNs this number of times, okay? Instead of that, you can just input one image and then you can get the final segmentation map, okay? So that could be done using this transposed convolution operation, okay? And this is the example code to train the encoder-decoder architecture, okay? You can see that these different types of network could be trained using the similar code we saw before, okay? These three lines, initializing the optimizer and row stop backward and optimizer.step, this code is not changed, okay? So anyway, you can train the encoder-decoder network using this code. And the next thing I want to tell is the pose estimation task, okay? In pose estimation task, we want to estimate the key point, their locations, okay? Or we sometimes reconstruct the 3D meshes, but this is rather complex. So we will explain you how we can estimate the key point of the images, okay? So for example, here we have input image and we have to define their each key point XY coordinate, okay? So head, top, neck, we define anyway 14 joint, and we have to label their X and Y coordinate, okay? That's actually the ground truth output. This is the pose estimation task, okay? So we can train our network, CNN network, by inputting this input image as the input to the CNN, and we can estimate 14 multiplied by 2-dimensional output. So 28-dimensional output, okay? And we can supervise each output using the MSE rules, maybe, okay? So this is the one simple implementation of the pose estimation. Okay, so we can apply L2 loss, which is the MSE loss. Okay, you can train the CNN network to output proper output for input image. Okay, but this type of heat map representation is non-effective compared to this kind of, the coordinate estimate. We can directly estimate these dimensional floating values, right? But rather than that, we can also estimate this type of heat maps. Okay, so for this region, this is having hand, right? And we can make this number of heat maps having this representation. So we can make heat maps having the location of each joint, right? Like this. So for the center point, that is the ground truth location, but we can apply some Gaussian blurring for that center point and make this type of heat maps, okay? And then can apply to estimate this type of output. We can enforce the network to output this type of heat map rather than directly estimate this type of floating vectors, okay? So it is known that in pose estimation, this type of heat map representation is rather high dimensional, but is more effective than the direct coordinate output. So people often use this type of heat maps, okay? And this is the example code to output that heat maps, okay? So actually, this paper is published in CVPR 2016, and this is their code. And yeah, actually they define several convolutional layers, and in the forward function, they apply those several convolution operations, and also they apply the nonlinear layers after the convolution operation, and they apply max pooling in the middle, right? And by applying those things, they extract some feature vector in the middle, and at the same time, they estimate the first heat map. This is the first heat map. And again, they concatenate the feature vector they obtained in the middle, and the initial heat map, they concatenated to make the signal, input signal again, and apply the convolution operation and estimate the second heat map here. And by doing the similar thing, they obtain the final heat map. Okay, so this is what this long code is doing. They apply several convolutional operation, nonlinear operation, and max pooling on the input image. And first, generate some feature vector in the middle, and also map it towards the heat map. And then iteratively apply similar operation to output the second heat map and the final heat map. And they apply MSE laws for these 3 heat maps with the ground truth heat map. And this paper is insisting that by applying this type of iterative convolutions, the performance is getting better, okay? So this is one example of the code for achieving the pose estimation. Okay. So given the coordinate, XY coordinate for 14 joint, actually there are this number of floating values indicating the coordinate of the each joint, 2D coordinate of the each joint we are having. And from this value, we have to make the heat maps like this. And this becomes the ground truth. And we made this type of network and have to train this network parameters by applying ground truth heat maps to the intermediate output. Okay. Then if the new input comes, the network can output the new heat map for that unseen testing images. Okay. So this is the example for the pose estimation, and this is the example for the semantic segmentation. So for undergraduate courses, I'm actually using this code, and yeah, this kind of thing could be the assignment one, but this time, yeah, I will not do that. And actually, the code assignment will have the different thing. Okay. Anyways, this is how we could achieve the computer vision applications such as pose estimation and the semantic segmentation. Okay. The thing which is important is make some differentiable layers to achieve the that application was required. Okay. Okay. So everyone following me? Okay. So actually, this is the end of today's class. Okay, let's finish here, and please prepare for Wednesday class, please. Okay. Okay. See you this Wednesday. Thank you.